So, hello guys, today I'm going to present FastInst, simple query-based model for real-time instance segmentation. So it has three key contributions. The instance activation guided queries, they propose instance activation guided queries. So they dynamically picks the pixel embeddings with high semantics from the underlying feature map as the initial queries for the transformer decoder. And they proposed draw path transformer decoder, in which we update the query features and the pixel features alternately. And they also propose ground truth mask guided learning, which prevents the masked attention from falling into a suboptimal query update process. And in this result, on V100 GPU, as you can see from the results, FastInst performs better than in terms of AP score, as well as in terms of the inference time, as can be seen here. So let's go into details. First of all, about the overall architecture, it contains three main parts: the backbone pixel decoder, this is this guy, and dual path transformer decoder. So in backbone, we simply take input image and generate three feature maps of the resolutions of following resolutions of the input image. And then from the backbone, the pixel decoder aggregates the feature maps and outputs three multi-scale feature maps. And from the middle size, this E4, middle size feature map, we generate n instance activation guided queries, and we concatenate it with some auxiliary learnable queries to get total queries Q. So this is NB auxiliary queries and instance activation guided queries from the E4, concatenate them and pass it to the transformer decoder. And transformer decoder additional takes in small size feature map, which is this E5, and also queries obtained from the pixel decoder to update in dual pathway, which I will explain later. Then predict the object class segmentation mask at each decoder layer. So let's go to pixel decoder. So for simplicity, for improved performance and less computational cost, they decided to use PPM FPN, which is parameter pooling model of feature pyramid network, to enlarge receptive fields and also to improve performance and to have less computational cost. And they also shows results about this, why it's better than the others in terms of the less computational cost. This is the pixel decoder. And next, the most important thing, instance activation guided queries. So the problem of the DTL models is their object queries are zero initialized. So it takes time to converge the DTL models. And the deformable DTL solves this problem by selecting query bounding boxes from pyramidal features. So FastInst, inspired by this deformable DTL, they pick the queries with high semantics from underlying multi-scale feature maps. So what they do is they put a auxiliary classification head on top of the middle size feature map, this E4, to yield class probabilities, including no object class, for each pixel in that E4. And this auxiliary classification head is composed of two convolutional layers and softmax layer for generating the probabilities at the end. And from there, they pick n pixel embeddings with high foreground probabilities as object queries. This n, they chose it to be 100. And yeah, then to supervise this auxiliary classification heads that provides us some useful probabilities, they use matching-based Hungarian loss, in which they use location cost, complete assignment. So this location cost is a simple cost function. It's defined as an indicator function that's 0 when the pixel is located in the region of that object, otherwise it's 1. And the intuition behind this cost is that only the pixels that fall inside that object can have a reason to infer the class and the mask embedding of that object. So basically, these dots can be called as queries. So if this dot is in the object of interest, its location cost will be 0. And if it is outside of the object, if there's no object is here, then it's gonna be 1. So we want to decrease this loss so that all the queries are focusing on only the object of interest rather than no object. Next, now we come to the dual price transformer decoder. So from this IA guided queries we got from this E4 with auxiliary classification head, we concatenated with some learnable auxiliary queries, this MB, to obtain total queries Q. Why do we use auxiliary learnable queries? The reason is we want to facilitate grouping background, as they claim, grouping background pixel features and provide general image independent information in the subsequent dual update process. So now we come to the dual update process. So we get this E5 from this pixel decoder and we flatten it, and we take this Q coming from the concatenation of IA guided queries and auxiliary queries, and we fed it into decoder. And each decode layer updates this pixel features and the Q like EM, the expectation maximization cluster. So in each step, we update the pixel features according to centers or queries they belong to, and the M step will update cluster centers. So we first update pixels, then we update the queries. And how this update process works, I will explain next. So how do we update this pixel and queries? It's actually giving in this pixel, also in this pixel. So first we add positional embeddings to the pixel features, and we fed it in the cross attention and this fast forward network layers. But we don't use self attention in this one because it introduces massive computation due to the long sequence lengths of pixel features here. So, and here we use mask attention, as can be seen here, followed by self attention here. And this mask attention is useful because it restricts the attention of each query to only attend within the foreground region of the predicted mask from the previous layer, and the context information is hypothesized to be gathered through following self-attention here. So basically we use the predicted masks to mask attention to perform the self-attention in the next stage. And I will explain about this later. But this is not sufficient because as you can see from this picture, our predicted masks are not so perfect. So we miss some of the pixels here. So it's possible that the transformer decoder will go to a suboptimal update process. Because of this, we miss some of the parts of the features that we need to do self attention. So to prevent this, they propose ground truth mask guided learning. So what it does is it replaces the predicted mask used in the else layers mask attention with bipartite mask ground truth mask. So basically, so in this else layer, we have masks, and this is the index of the mask, the queries. So if this I and J is matched in ground truth mask, we use ground truth mask, or we just use the predicted mask, as can be seen here, to in order to prevent the suboptimal corrupted processes. And the loss function. So they use 3 loss functions. This LPET, this LPET is for the ground truth mask loss, and this LPET is the is all together. So this instance activation guided queries might say, what is this class Q? So this class Q comes from this auxiliary classification head that we want to optimize. So this is the classification head for raise. So we perform loss on top of this. This is simply a binary cosine interval loss, and we have additionally CE loss. This is the loss from main classification head coming from on top of transformer decoder layer. This D stands for the number of decoder layers. So at 0, you might say, what happens at 0 index? So in 0 index, we don't pass to the decoder layer. So we simply use this loss, this IAQ loss. And in the next stages, we pass to the decoder layer and we perform this cosine interval loss, dice loss, and the classification loss, respectively, for each decoder layer. And this one is for ground truth mask guide loss. It's the same as this loss, except that it doesn't count this zeros indexed loss. It only counts the others. So yeah. So now we go to the experiments. So we have D1, D3. This D1 stands for 1 decoder layer, and this stands for 3 decoder layers. And as can be seen from the results, that we pass these methods in terms of AP, but we can't pass this mask to formula and FastInst. But compared to them, their FPS is very low. Our FPS is much higher, and it's actually highest among these methods. And then we change the backbone to R101, and for obvious reasons, our FPS decrease significantly because we are using bigger backbone, but our accuracy is actually better than D1, since we are comparing with 1 decoder layer with 1 decoder layer. And we have, of course, if we use bigger backbone, we have a better AP score, which is better than this 3 decoder layers with R50 backbone layer. Then, and this one is the deformable convolutional. R50 is deformable convolutions, and so as can be seen from this, we use R50 descent, our FPS decreased slightly from 53 to 47, but our AP significantly improves, as you can see from these results. And if we use 3 decoders, and of course our FPS decreases, but still this is real-time FPS. We consider above 30 to be real-time FPS rate. And this is the first time that they say that our AP score becomes more than 40. None of these methods, as can be seen here, has AP score of 40 except this guy, but its FPS is not that great. And some ablation studies they performed, they checked how does this AI-guided queries work? And as they found out that especially when the transformer decoder layer is small, it performs much better than zero initialized or learnable or resized queries. There's a jump around 1 AP jump. This implies that FastInst does not require a lot of decoder layers to process. So decoder layers itself takes a lot of computation. So they decrease this computational cost by offering this AI-guided queries. And however, if you use more decoder layers, the AI-guided queries is not that useful, as can be seen from there. The accuracy is slightly improved. So yeah, this is good for decreasing decoder layers. And now let's go to the table 3, the draw pass update strategy. So they, as I said before, they update the pixels, the inquiries, and they checked it whether it's the same if they update query and then pixel, and they found out that there's not much difference between these two. And they found out that if they just simply update the pixel features for 6 decoder layers and queries for 6 decoder layers, the accuracy, the IP score is less than this approach. So this means that the dual update strategy works the best. And we come to the table 4. We have ground truth mask guided learning. So they've checked whether this ground truth mask guided learning helps to the accuracy. And it's doing well, but not so great. So I would say the ground truth mask guided learning is not that big of a main contribution. The main contribution of this paper, I would say, is this AI guided queries to prevent the network from using many decoder layers. They provide this AI guided queries, and also to have better FPS. And then about the pixel decoder, as you can see, if you use the bigger pixel decoder like MS deform attention, we have very good AP scores, 40, but if you check the FPS, it's 21. It's basically not real time. And the flops is much higher than the other people. And if you use FPN alone, it doesn't actually do well in terms of AP, but if you use PPM FPN, the parametric pooling module FPN, then our accuracy is slightly better. So yeah, that's all for me. If you have any questions,